Okay, folks, I'm going to briefly describe the different types of work that we can come up with relevant to chemistry. This isn't necessarily an exhaustive list, but it's the big ones that we often come across in chemistry. So going back to our definition, work acting over a distance, and being a little bit more precise with the way that I'm defining it here, dW equals negative absolute value of F dz. So let's unpack that just a little bit here. So, and I'm going to rewrite that over here where I've got a little bit more room. So there's a couple things to note here. So dz is my change in distance, right? The distance has to be changing in order for there to be work. So this absolute value of force, so that is an external force being applied, and the negative sign there is a convention. And the idea is the following here. If the change in distance is positive, so in other words, it goes from zero distance changed to some amount changed, and we're using the absolute value of this external force, then because of that negative sign, this will mean that dW is negative. So what does that mean for the system? Well, that means that the work done is exothermic. So by definition, when our energies are negative, that is exothermic. So work in this case is leaving the system to the surroundings, which is exactly what we want to indicate here. So if we've applied some force over a distance and that we get this negative value here, that's telling us that the system is working on the surroundings. So this is easiest viewed when thinking about expansion. And we'll go through this in some more details in a moment here. But if we can imagine, right, if the volume of something expands, and we've got that negative sign right there, that tells us that the system was working on the surroundings. Or if the volume compresses and now dV is negative, that's a negative times a negative, so that tells us the surroundings were working on the system. Okay. So, and again, going through these examples, so I just talked about the work example, or the expansion example. And you can see here with the units, if we look at this here, I'm just going to write P dV to keep this simple. That is a Pascal per meter cubed. Recall a Pascal is a Newton per meter squared times a meter cubed. That's going to give me a Newton meter. And if we go back to the very top here, Newton is our standard for force. Meter is our standard for distance. So Newton meter gives us a joule. Okay. So surface expansion, or sometimes surface tension, is another type of work. So surface tension is the work required to bring a molecule across an interface. So if we imagine we've got a gas here and a liquid, and I want to take one of these gas molecules and pump it into the liquid, or the other way around, we've got to break that surface. So we've got to apply some force over this distance across the interface. Okay. So that surface tension is given by gamma, and this is related to the change in area. So you can see with the units there, that's going to be a Newton meter is the unit of surface tension times a meter squared. That gives me a Newton meter, or a joule. So extension, this is very similar to just our nominal definition of work, where F is our tension in units of meters, and dL is some change, or in units of newtons, excuse me, and dL is the change in length in meters. So we can see right away that's going to give us a Newton meter, or a joule. And the last one relevant to chemistry is electrical work. So the force that we're applying here is the force required to push an electron through some potential barrier, given by phi. Okay, so if I look at now phi dq, capital Q for change in charge. So potential has units of volts, charge has units of coulombs, and if you recall, a volt times a coulomb gives me a joule. Okay. So we're going to get into a lot more detail on expansion work, but I just wanted to mention briefly these other types of work and that we can apply the units and the equations to get the right values. Okay, I'll see you in the next one.